Application Insights provides the APM capabilities in Azure Monitor by tracking server response times, application performance metrics and failures, performing availability testing, dependency tracing, and much more. Application telemetry is forwarded from your application code to an Application Insights resource, and from here, you can monitor, troubleshoot, investigate, and perform forensic analysis using curated App Insights views in the Azure portal. Or you can access the raw metrics and logs in Metric Explorer and Log Analytics respectively. I'll begin by showing a dashboard as the starting point to drill into Application Insights. This is the default application dashboard and has a summary of many APM KPIs grouped into domains. Usage, reliability, responsiveness, and browser performance are the main areas, but it also includes shortcuts which allow me to navigate directly to my App Insights resource or specific App Insights blades. I'll kick things off by drilling into the application map. App Insights uses distributed tracing to track dependencies across multiple app components and backend services in microservices environments. One of the ways distributed tracing data is used is to automatically build an application map to show who's talking to whom and which components of the app were dependent on others during a given time period. No manual effort was required to build this view. Simply enable App Insights monitoring on your app components, and App Insights takes care of stitching together the traces to generate the map. Each circle on the map represents an independent application component that's a part of a larger distributed microservice application. These components may run on any number of instances, hence the instance count of each app component may vary. Moving from left to right, you can first see client-side telemetry and availability tests, then application instances are in the middle, and finally backend dependencies are over to the right. In this map, those dependencies are Azure storage resources and databases. The arrows represent the number of calls between the components, and they're labeled with the response times for those calls. Red coloring indicates failures and also shows the percentage of failed versus successful requests on the calls. This application map is also a starting point for investigation. I can highlight a single app component, and I'm shown options to look at performance and failures in more detail, or I can switch tabs and move over to infrastructure to see more info on where the app is running. I'll click on Investigate Performance to drill in. This takes me over to the Performance blade. This view lists server-side operations and dependencies by their duration, and has a toggle to show browser page views and dependencies as well. You can filter by a single operation name to change the scope of the data displayed. I'll select Get Home Index because it's the slowest one, and all of the tables and charts are updated to reflect the selection. Next, I can use the histogram in the top right to filter down only to slow cases of the operation where I get to define slow. And this limits the operation shown now to a much smaller subset than where we started. I then have the option to look at groups of transactions with commonalities or drill into individual transactions. I'll click on the suggested example to get down to the end-to-end transaction view. This is a Gantt chart showing where my transaction spends its time per dependency and includes exception details and the call stack to investigate more in the event of failures. Based on this view, I can tell none of my dependencies is responsible for the poor response time. So it may be something related to the application code itself or the infrastructure resources where the app is running. If it's a code-related issue, maybe I'd open a work item for the developer. But here, let's continue investigation for now. I'll drill into the profiler traces, which gives me finer granularity into the classes and methods used by the transaction. The profiler is collecting sample traces on a predetermined interval, and you can also configure it to run based on CPU and memory triggers. I'll select the sample transaction from the slowest ones on the left-hand side. And we can see that the bulk of the time was spent not processing, but just waiting for resources to become available to continue its processing after. Now this points us to some resource constraint on the infrastructure side. So I can return to my app map to see where the app component is running. The app map allows me to see the resource details, and in this case it's a VM. Specifically, it's the retail VM 01. Now I can go to this VM and look at its basic resource utilization, items such as CPU, memory, disk, and network I/O in the form of time series metrics to find any underlying issues. Or if your VM is forwarding performance logs to Azure Monitor logs, just as your app code is forwarding logs to Application Insights, you can use log analytics to do a more deep dive analysis and look for correlations. This is a key workflow that's available when all of your resources have been configured to emit logs to centralized workspaces where ad hoc statistical analysis and machine learning can be used to reveal unexpected relationships and patterns. To start this workflow, I'll navigate to Logs. The UI will automatically be scoped to logs just for the VM of interest, and I'll be presented with a set of related example queries. I'll go ahead and look at CPU over time just to see if there's anything obvious that jumps out at me. As it turns out, we do see a spike to 100% CPU usage periodically. And now that you've seen just how easy it is to get started with example queries, I can use a couple of queries that my team has written to do the type of visual correlation analysis that I mentioned earlier. The first thing I'll need to do is switch the scope of the Logs UI from the VM to the Log Analytics workspace, which contains logs coming from a wider range of resources. And this is also where my team's queries are stored. The query that I'll start with looks at CPU usage by process. And here's our culprit process, causing the repeating CPU spikes that we saw earlier. And the query below looks at app response time and CPU usage of the problematic process on the same pair of axes, but now it's going to be scaled appropriately, using tens of milliseconds for app response time and CPU from 0 to 100%. And this definitely shows there's a clear-cut increase in app response time every time the previously identified process pegs the CPU at 100%. That's the root cause of the application performance problem in this example. The performance blade looks at operations and dependencies from the context of duration and response time. That is, how long different transactions take to complete. But now we're going to move on to failures. These are the transactions that fail due to exceptions and timeouts, or for some other reasons, the transactions end prematurely. Again, I'll start with the application map, and I'll look at a component that's showing failures. I'll select it, and now I'm presented with the option to investigate the related failures, or I can take a step back and simply click on the failures blade to get to all of the failures that occurred without filtering based on the app component. On this screen, among other criteria, I can filter by operation and exception type. These filters limit my dataset to the subset of operations shown below from the drill into button. In this example, it's about 290 odd exceptions and about 14 debug snapshots that match my selections. Now I can select a single sample operation to see its end-to-end transaction view. This is the same view that we used to analyze performance before, but now I'll focus on the exception causing the failure. I can click on the exception to view its details and the call stack leading up to it. And depending on what I find here, I can choose to open a work item and assign it to the appropriate developer as part of my DevOps process, or if I'm familiar with the code myself, I can open the snapshot right here, right now. I'm presented with a call stack, and I can highlight the individual methods to see the function arguments and local variables. And this level of troubleshooting detail is only available if the APM tool being used to do the monitoring has the option of collecting snapshots in the event of failures. So as I start clicking through the methods here, you'll see that we're missing the value of a local variable. And if I go far enough back in the stack, I'll find the root cause in this address validator function where an alphanumeric is being used for the zip code instead of an integer as required. There are also options to view the decompiled code or download the entire snapshot into Visual Studio for further analysis. So now you've seen how to do performance analysis and failure analysis based on historical data for the last 30 minutes, 1 hour, or for even longer time periods. Let's pivot to start performing real-time analysis on the last minute's worth of live data, down to 1-second granularity. Live Metrics enables you to track incoming and outgoing requests and overall health. This blade also provides a list of sample telemetry that can be used to view traces, dependencies, and failures, with some additional detail if you decide to click in. You can also filter the Live Metrics view by a server of concern for a smaller scope of real-time data. The only limitation here is this view only holds 60 seconds worth of data, but you can pause it at any time for a snapshot if something interesting occurs. In the previous workflows, I performed troubleshooting and investigation on demand. I started by looking at application performance as a whole, and when I saw something anomalous, then I drilled down and used filtering to identify the specifics of the problem. This is a great capability, but I'd like to point out that it's very reactive. An operator or analyst has to navigate the UI to observe and isolate the issue. Smart detections, on the other hand, are automated warnings about the performance problems and failures occurring in your app. They identify failure anomalies by using machine learning to determine the expected value of the number of failed requests, and it uses historical baselines to detect performance anomalies such as response time degradations and memory leaks. Also, depending on the type of detection displayed, there'll also be a count of the affected users that helps you gauge the extent or the impact on your application's users. You can click into any of these detections for more details, including the ability to see the underlying log query used, profiler traces, response time reports, and the request properties. Smart Detection is a great tool and provides very meaningful automatic trend analysis and anomaly detection. But at the end of the day, you also need the ability to create your own alerts based on signals and thresholds of interest for your organization's use case. Alerts meet this need, so I'll move over to the Alerts blade. Now you can get an across-the-board view of all alerts in a subscription, filter to those alerts tied to a resource group, or to those alerts from a specific resource, all within a user-defined time range. These alerts are displayed by severity, and you can drill into the details for all alerts or just for one severity level. I'll click into my Sub1 alerts. Each row shows the alert details, starting with the name and severity, and going on to describe the monitor condition. And this is whether the alert is in a fired or resolved condition. This is different from the alert state, which is managed by the operator and can be manually switched to acknowledged or closed as part of your escalation or resolution process. Now I'll walk you through the process of creating a new alert. First, I'll go over to New Alert Rules to get started. Notice that the scope of the rule is already pre-populated with the App Insights resource where I started, so the context has already been passed in. Next, I'll set the condition under which my alert will fire. Here's a list of all of the available signals from App Insights, and they can also be filtered based on metrics, logs, or activity log. I'll use exceptions for this example. This shows a historical view of exceptions over time, so I can see the metric values that have recently been collected to better inform my choice of the threshold. And if the metric you're using supports dimensions, you can filter your alert rule to use one or more of the dimension values. In my case, I can decide whether I want to look at all exceptions, or just those exceptions from the app running on the VM, or exceptions from the app when it's running on the app service platform. Now I can move on to setting the threshold. This can be a static, one and done, fixed type of threshold, or I can use dynamic thresholds to determine the threshold automatically based on past data. Dynamic thresholds also have flexible sensitivity where you can choose high, medium, or low to adjust how tight your threshold adheres to previously seen values. Note that there's a preview above where you can see the value being set by your dynamic threshold. You can also reduce the amount of noise generated by the alerts in a few different ways, by configuring the aggregation period, the frequency of evaluation, or the number of times the condition must be met before the alert is fired. Lastly, you need to set the action or set of actions that will be taken when the alert fires. This is done by setting the action group. These can be configured in advance or on the fly while you're creating the alert. The choices here include the typical email and SMS notifications, but also extend to executing runbooks or opening service tickets, or to more custom actions such as calling a logic app, a webhook, or a secure webhook. Up to this point, I'll focus mainly on the back-end application performance, what's happening in the application code, or what's happening on the infrastructure hosting the app. But App Insights also provides great visibility into end-user behavior. Usage Analytics enables you to answer common usage questions, such as which web pages and features are the most popular ones by the number of users, sessions, or events, where do users typically drop out of the website or business funnel, how often and at what time intervals do users return. With this type of information available to you, you can better determine when and where to assign development resources and align your development strategy with the desired business outcomes. I'll start with the most basic usage view called Users. Here, I have the flexibility to choose the time range of interest, let's say 3 days, and the data is first displayed as the number of users over time. But I can then split or segment that data using other properties like country or region, for example. Additionally, we can view more information associated with these users. Geographic location, OS platform, and browser version are being shown here, but you have lots of other options. You can also have the option to look at your user journeys by selecting random users or from your most active users. Select a single user to view their timeline, the number of sessions, pages viewed, and any clicks that are being tracked as events. In contrast, the single user timeline, which is very narrowly focused, User flows offer a more generic picture of where users go next. Instead of looking at what a single user is doing, user flows construct a visualization of the session flows for all users. It shows the subsequent series of pages and events used based on an initial page or event that you get to select. In this example, I've started with the home page, and now the home page becomes the first point of entry for this user flow. From here, you get a quick high-level view at the user path for many sessions at the same time. In this view, you can discern where users go next from specific pages on your site, where do users typically leave with the session ended, or are there any places where users perform the same action repeatedly or loop through the same series of pages. Application Insights data is also available in out-of-the-box workbook templates. Workbooks allow you to query data from multiple sources in Azure, create custom visualizations for reporting and analysis, and combine multiple UI elements into a single interactive experience. You can access the Workbooks gallery directly from your Application Insights blade. This is a collection of predefined workbook templates focused on application availability, performance, and usage that you can take advantage of as is, or you can edit them and customize them to better meet your requirements. Some of the more common examples are the failure analysis or the application index workbook. But let's take a look at the performance analysis workbook to get started. It shows a count of operations and their response time by average values and percentiles for multiple application insights resources all in the same report. And this is only the starting point because each of these templates can be edited for content and visualizations. The editing capabilities include access to the underlying log analytics platform, where queries can be updated or rewritten from scratch depending on the objective of the workbook. While workbooks provide great at-scale interactive reporting, dashboards are near real-time views that allow you to monitor resources and quickly launch tasks for day-to-day operations. They can also be customized to meet the needs of various user roles and shared across teams in your organization. The benefits of dashboards include automatic refresh intervals, standard Azure role-based access control, and more. However, the key point about this particular application dashboard being shown now is the fact that it's available out of the box and doesn't require any user input. All of these tiles are automatically based on the telemetry being sent to your application insights resource. In addition to the workbooks and dashboards shown just a minute ago, you also have the option to monitor the status of alerts and resource health of the entire resource group where the application insights resource is stored. This view displays all of the resources grouped by type and their related alerts divided by severity. Next, I'll show the option to include the resource health status on the same table that has all of the alerts and all of the links to drill into insights associated with specific resources. Finally, this view also has the option to navigate to an application map. The main difference here between this application map and the one that we showed earlier is that this map is much wider in scope. It includes all of the dependencies related to all of the application insights resources in the entire resource group, whereas the earlier version was much narrower in scope and only focused on dependencies associated with a single application insights resource. I'll end the demonstration by highlighting that workbooks aren't limited to App Insights data, but can also be launched directly from Azure Monitor. Azure Monitor receives metrics and logs not only from the app layer, but from the guest operating system, Azure resources, and the Azure platform. You can see that the Workbooks gallery now lists templates for other infrastructure resources, such as virtual machines, storage accounts, databases, and more. Of course, App Insights related workbooks are still present, but they're now among many other templates available in the gallery. Remember that workbooks provide at-scale views with the option to drill down into the details of one resource at a time. Here, in the Application Failure Analysis workbook, I can choose several App Insights resources, a time range, and evaluate failed versus successful requests, trends, and any affected users. That wraps up our overview of Azure Monitor Application Insights. Hopefully, you can leverage what you've seen today to take advantage of these capabilities.